Let's now discuss the elastic displacement of an axially loaded member. So using Hooke's law that we learned about in Chapter 3 and the definitions of stress and strain that we learned about in Chapters 1 and 2, we can develop an equation that can be used to determine the elastic displacement of a member subjected to axial loads, purely axial loading. Consider this general scenario of the bar shown, in which the values of internal axial or normal force, cross-sectional area, and modulus of elasticity may vary along the length of the bar. Okay, so the normal forces or axial forces can vary. It can have a varying cross-sectional area, so it's a tapered member. It could even have varying materials, so different values of the modulus of elasticity. We can assume that the bar will experience uniform deformation and therefore uniform normal stress. To derive the equation used to calculate relative axial displacement of one end of the bar to the other, that is, an equation for delta axial displacement, we can isolate a differential element from the bar whose length is dx, cross-sectional area is a of x, and elastic modulus is e of x. So remember, we're keeping things very general. The cross-sectional area could vary as a function of x, the length along the bar. The elastic modulus could also vary, so e could be a function of x. So here is that little element here, a differential or infinitesimal element, taken from some part of the bar here. We're applying the method of sections here and here, isolating a little element here, a differential element of some infinitesimal length or width. Okay, that original length is dx, that infinitesimal length. Acting on the element is an internal axial or normal force n of x that depends on the length x along the bar, which causes deformation of this element into the dashed outline shape that you see here. Thus, the element undergoes an infinitesimal axial displacement d delta, and the stress and strain in the element are therefore as follows. So sigma, as we learned in Chapter 1, is internal normal force over cross-sectional area, which in general are both functions of x or could be functions of x. So sigma is n of x over a of x, and from Chapter 2, epsilon normal strain is the change in length of the element d delta over its original length dx. If the material behaves elastically, meaning it has not yielded, then Hooke's law applies, as we learned about in Chapter 3, where e, the modulus of elasticity as a function of x, in general equals sigma over epsilon, normal stress over normal strain, or rearranging sigma normal stress equals e of x times epsilon. Okay, therefore we have the following, where we have our expression for sigma equals e of x times our expression for epsilon. Rearranging, we see that d delta, which is the differential amount of the elongation or the displacement of this element, d delta would equal n of x dx over a of x e of x. We can integrate each side of the previous expression for d delta, which was this one here, to obtain an equation to calculate the total axial displacement of the bar endpoint to endpoint, that is from 0 to L. Okay, so here's that fundamental formula for axial displacement. Delta equals the integral 0 to L, n of x dx over a of x e of x. To be very clear, let's define each of these parameters. Delta is the displacement of the right end of the bar relative to the left end, so one end relative to the other end. L is the original length of the bar. N of x is the internal axial or normal force at the section located a distance x from the left end. A of x is the cross-sectional area of the bar expressed as a function of x, and E of x is the modulus of elasticity of the material expressed as a function of x. Occasionally, we need to calculate the relative axial displacement between 2 points A and B on an axially loaded member that are not necessarily the endpoints. They could be any 2 points on the member, in which case the limits of the integral would then vary from point A to point B. So here's another expression of the relative axial displacement formula. Delta sub AB equals the integral from A to B, n of x dx over a of x e of x. In most cases, integral calculations are not actually required here, as the above formula reduces to a simplified version when applied to the most common loading scenarios as discussed next.